Hello, statistics student. This video is for chapter 2.7, part 3 of standard deviation or measure of variations. We talk about standard deviation, how important it is in terms of describing how data varies. And the good use of it is you notice that if you are able to have the mean being in the number line of your data, like imagine this is like a dot plot or even a histogram, then you can have mean in the middle, and then you have two tick mark. Each tick mark is one standard deviation away from the mean. Then this pretty much include all your data. And this example is a good illustration. So we have two standard deviation below the mean, 9.09. Two standard deviation above the mean is 11.97. And so what we can do is, and D is how many data are two standard deviation below the mean or two standard deviation above the mean. So after we calculate the the boundary of two standard deviation, this is 11.97. So any data that is higher than 11.97 is two standard deviation above, but we don't have anything that is beyond that, right? So that's zero data. What about 9.09? Is there any data that is below 9.09? It's 9. 9 is below 9.09. So we do have one data, 9. How many data? How many? One data. The data of 9 is two standard deviation below the mean. So that is a good use of understanding what is standard deviation. If you see data that is two standard deviation away from the mean, you know that it is unusual. And anytime you see unusual, that is statistical significant. Okay, so we'll continue to talk about standard deviation being like you can think of it as a measuring ruler to not classify, but to include, to understand the spread of your data. So it's like a tick mark on the horizontal axis. And it can be used to describe how data away from the mean. So we would say a sample data, you can think of any sample data would be thinking of as a mean plus a number of standard deviation times the standard deviation. So any data that you have, if you draw the number line where this is dot plot, this is X bar. If I have a data value, I can understand this data value not as a absolute data value, but as, oh, how many times are you from the mean? Okay, if I put my tick mark of standard deviation like this, then I know, oh, this is 1 point something away from the mean, above the mean. If my data is here, my data is 2 below the mean. So it is important to identify data value that way rather than knowing what value it is. So you can use it to compare relative standing, right? So if you have two sets of data, you can compare how much the data is from the respective mean. Okay, so in order to do that, we have something called a z-score. Z-score is the number of tick mark a data is from the mean. Meaning, if you have a data value is at this point, two standard deviation away from the mean, we say z-score is equal to -2 because it's -1, -2. This is z-score 1. One standard deviation is z-score equal to 1. Two standard deviation is z-score equal to 2. 1 point something would be 1 point times standard deviation away from the mean. Okay, so z-score would be defined as how much you are from the mean divided by the tick mark of sigma or S. If it's a population data, we use sigma. If it's sample data, we use S. The round-off rule for Z is 2 decimal places. This is more historical than anything. It's just that in the old day, we have tables of z-score and they're all 2 decimal places. So z-score tells us how many standard deviation away data is from the mean. Negative means it's below the mean. Positive means it is above the mean. And z-score has no units. It's a tick mark. Okay, how many tick mark it is from the mean. So let's do an example. What is this example? Oh, here I didn't read it. So a student has an English score of the score is 83, but in the class of English class, the mean is 80. The standard deviation is 10. So that is 83 is English. This is the mean of the English, mu of English. And then S of English, right, is 80 and it's 10. So this person 83 is pretty good, is a little bit, is 3 points above the mean. But another student's history is 75 score. This is history. But this history class mean, sometimes when the class actually is not as doing as good, so we say mu of history is 72. So this person is also 3 points above it. Do they score the same? And then the mu, this is no mu, sigma of H is 7. Oh, I should not say S. I should say sigma, right? Because it's a population. It's the whole class is population. So which one score better? Both of them score 3 points above the mean. So let's use z-score. Z-score the way to do z-score is the x value minus the mean divided by sigma. So you do 80 for English. Z-score of English is 83 minus 80 divided by 10 is 0.3. For history, it's 75 minus 72 is also 3 in the top, but your standard deviation is shorter, it's 7, so it's 0.43. So for the English score, this person had the mean is 80. 83 is less than 1 tick mark, it's 0.3 tick mark, right? But for the English, the mean is 72. But then tick mark is lower, but the tick mark is 0.4. So it's a little bit more. Well, I think this 0.4 is actually less than a half. So it's 0.4 is better than 0.3. So the student score less than 1 standard deviation from both the mean, but 0.43 is greater than 0.3. So score a little better in history. So you can use it to understand relative standing. Another example. We have measurement of diameters of bottle caps. Some factory manufacture bottle cap for water or soda, right? So they measure the diameter. What situation is best? Do you want the bottle cap diameter, like they manufacture a lot of them? What a size of a bottle cap? 1 cm, 2 cm? No, 1 cm is too small. 2 to 3 cm, right? 2 to 3 cm. So this is a diameter, maybe 2 cm. So because you are manufacturing it to use for in a factory, everything in the factory manufacture should be exactly about the same, right? Because it's used for like water bottle. So they should have low standard deviation. They should not vary too much. Otherwise, you cannot fit into a bottle. So for the manufacturing, you want low standard deviation. Okay. In other cases, maybe high standard deviation is good. The last things we want to analyze is how to find out standard deviation or how to compare standard deviation when I look at two histograms. These are not data. If I have data, then I can tell, oh, they are apart from each other, they varied a lot, then I have high standard deviation. If I have a histogram, how do I tell who has higher standard deviation? So let's look at these. So presumably they have the same scale. I don't know why this scale is in the top. So they are all have about 50 being the mean. So this is 50, right? This also has a 50 being the mean. But these range is from 40 to 70. This range from 10 to maybe 100, or 90, 100. So these are almost spread out. They have less data in the middle. This has a lot of data, 40-something data in the middle, which has higher standard deviation. Higher frequency means data are clustered together, right? They cluster around all 50, 50, 50, 50, 50, 50. Don't change. And then the highest you can go is this. These are very spread out, right? So 50 only have 10 data, and then there you have a lot of 40, you have a lot of 70, 80. So the second graph, this one, has higher standard deviation. The bars is low because it's low frequency. There are more varies. Data values are more varies. Values are far away from the mean. So see how far this one is from the mean? Whereas these, they're very close to the mean. Okay, so that's how we understand variation. Two important concepts is large number means large variation. Small number means small variation. Most of the data is 2 standard deviation above or below the mean. So that is all of 2.7. Do we have another one? Oh, we have the last part, which is empirical rule. So maybe we will talk about this. I can finish this really quickly. So empirical rule is a way to understand how you can use standard deviation to describe the percentage of data within 1, 2, 3 standard deviation from the mean if the data is bell-shaped. Okay, so this is on the assumption that your data is bell-shaped and symmetrical. So we call it normal distribution, bell-shaped and symmetrical. Normal distribution. And then what we say is if we write the data, draw the data like that, mark the data value. So this is the mean. This is 1s. This is 2s, minus 1s, minus 2s, or mu, sigma, right? Sigma, 2 sigma, like that. What happens is if these are symmetrical, that means the histogram are like this. The number of data within this range, the number of data within 1 standard deviation from the mean is 68%. 2 standard deviation is 95%. 2 standard deviation is 95. This is 68%. That many data is 95%. So that's why I say it's very rare to have data above beyond 2 standard deviation. And then 99.7 data is 3 standard deviation. 99.7, more than 99.7 data is within 3 standard deviation of the mean. So we call this 68, 95, 99.7. In this book, they call it more than 99, but yeah, we can do that. So let's do an example. It's very easy, but you have to make sure that it has bell-shaped distribution, and you have to know the mean and standard deviation. So people draw cash from ATM, and they say the cash withdrawal had a mean of $42 and a standard deviation of $6. So calculate the percentage of cash draw that falls between $30 to $54. So the way to do it is you draw a number line, always draw a number line, put the mean in the middle. The mean is 42. And then you do the 2 tick mark. Plus 6, what is it? 1 tick mark. 6 is the standard deviation is 6. Plus 6 is 48. Plus 6 is 56. Minus 6 is 36. Minus 6 is 30. So you can tell that this is, you do not use those regular tick mark, but then you do a bell shape here, and then you say 30 to 54. 30 to 54. Plus 6, plus 6 is 54 actually. So plus 6, yes, 54. So calculation. So this is how many standard deviation above and beyond. It's 2 standard deviation, right? 2 standard deviation that corresponds to 95% of data. So 95% of people, when they go to the ATM, they draw $30 to $54. So what about 20 to 60? 26, is it 24 to 60? 24 to 60. I don't think we have 20. Because if I do one more standard deviation, it should be 24, right? And then if I do one more standard deviation, which is 3 standard deviation, so that would be 60. I add 6, minus 6, minus 6, minus 6 is 24. So 24 to 60, that should be 3 standard deviation away, right? So that would be 99%. 99, more than 99%.